series of electric circuit analysis. So in the previous class we were discussing about the initial conditions and solution of equations. We have seen what initial conditions really mean and what is the history period of the system, where I represent the history period of system for t less than or equal to 0 minus, where t equal to 0 minus is the instant where just before the operating of the switch, and t equal to 0 plus is the instant where the switch is, or the state of the system or instant of the system immediately after the switch is operated. Okay, so also we have seen a resistor, a pure resistor. What are the initial condition in resistor? So we have seen in the yesterday's in the previous lecture that the resistance will not have any initial condition since it is not an energy storing element. Therefore, the initial conditions in the resistance is absent. Okay, today we will look into what are the initial conditions in an inductor. So let us consider an inductor of inductance L. Okay, let this be carrying a current IL, and the voltage across inductance, let me take it as VL. I will follow the passive sign convention. Okay, so I have an inductor of inductance L carrying a current IL, and the voltage across this inductance is VL. So the voltage across the inductance VL is given by VL equals to L di by dt. Okay, the voltage across inductance is given by L di by dt, and you should remember this, that the voltage across inductance is always a self-induced EMF across it because of the self-inductance L henries. So therefore, I gave the expression for EMF induced or EMF across inductor as the expression for self-induced EMF. So this L di by dt indicates the average self-induced EMF across an inductor over a period of time dt. Okay. Now, to be specific, it will be IL, dIL by dt. So here, there are two cases that the inductor may be connected with alternating current source and the inductor may be connected with a direct current source. Let us first understand what happens to this inductor when it is connected to a direct current source. Let this be connected through a switch. This is VDC, this is switch S. The same current IL. Okay. This is connected at the inductance L, and this is the voltage across VL. In the fundamentals of electrical engineering or basic electrical engineering subject, you studied what will be the voltage and current when the inductance is connected to an AC. Okay, there we have seen there will be lagging of the current by some angle. If it is pure, it will lag by 90 degrees. If it is a practical inductor with some internal resistance, it will lag by an angle less than 90 degrees. Now here, the switch AC is open initially. The moment I close this switch at t equals to 0 instant, always I consider the instant at which I close the switch as t equal to 0. Okay. Now when at t equal to 0, if the switch is closed, the current IL will flow through the inductance L. Now because the source is DC, the current flowing will also be DC. For an instant, I will forget about the transient condition. I will consider the steady state condition. That the moment I close the switch, the steady state occurs in the system and a steady voltage DC is applied. A steady current IL will flow through the inductance. Now this steady current IL flowing through the inductance is a constant current, and if I take the differentiation of that constant current, then it will be 0. Okay. So for DC IL, for direct current IL, my DL by dt is DIL by dt is equals to 0. Therefore, my VL is equals to 0. This is what? For DCIL at steady state. For DCIL at steady state, DIL by dt is 0 because IL remains constant. At steady condition, my IL remains constant. Therefore, differentiation of constant is 0. Hence, my VL becomes 0. So, what does it mean? So, what we mean by voltage becoming 0 across any element? We know that when the voltage across any element or any terminals is 0, I consider it as short circuit. So, here what is happening? When the direct current tries to flow through the inductance, the voltage across inductance becomes 0. Therefore, I can say inductor act as short circuit. Inductor act as short circuit under steady state. Under steady. So, for any DC given, inductor act as short circuit. Okay. So, that is why we generally say that the transformers are never to be connected with DC, as the transformer windings are inductances directly connected to DC. It will create a large current flowing in the transformer winding and it will burn out. I think you might have heard this when you studied this in the fundamental of electrical science. Okay. So, here the behavior of inductor under steady state condition is a short circuit condition. It is a short circuit terminal. This is what happens under steady state condition. So, let us see later now what is happening at initial condition. Now, this is about voltage at short circuit condition, at initial condition, at steady state condition, the voltage becomes 0. Therefore, my inductor is acting like a short circuit. If I have to give the current in inductor, so I have this expression VL equal to L DIL by dt. I will rearrange this expression and I would like to give the current expression as DIL is equals to 1 over L VL dt. So the expression is given by VL equal to L DIL by dt. I want DIL. So DIL equals to 1 over L VL dt. Okay. So if I want to have the expression for current, then I have to integrate this expression. So I can write IL is equals to, or IL is equals to 1 over L, where L is a constant self-inductance value, integration VL dt. 1 over L integration VL dt. Let me take this as equation. I have not given the equation number earlier. I will take this itself as equation 1. Or we will take this as equation 2. And the first equation, I will take this as equation 1. So IL equals to 1 over L VL dt. Now here, the limits of integration can be taken over a period of time. Now what is a period of time? So whatever the circuit I have considered here, I will redraw it instead of going up and down. I have VL here, this is L, this is IL, and the switch is assumed to be closing at t equals to 0. So the switch is operated at time t equal to 0 instant, but I don't know whether there were some initial conditions or not. So therefore, what I assume is, or what I consider is, this inductance is a energy storing element. Therefore, I can directly consider there can be some initial conditions present in this inductance. So the limits of this, time limit of this integration, what I will take is IL of t, I will write it as 1 over L integration minus infinity to some instant t VL dt. Why it is minus infinity? because I don't know since when the initial conditions or the previous state conditions are prevailing in the system. I don't know since when the existing conditions before the switching action has taken place are existing in the system. So therefore, I will consider some time minus infinity. So minus infinity doesn't mean real value of infinity, some time before t equal to 0. Now I will rewrite this integral in two parts. One, representing the system condition in its history period. One, representing the system condition from just before the switching operation to some time instant t. Okay, so when I write down, you will be clearly knowing this. So 1 over L integration, I will write minus infinity to 0 minus. In the previous lecture, we have clearly defined what 0 minus is. It is the time instant, okay, just before the switching action has taken place. VL dt plus 1 over L integration 0 minus 2t VL dt. So there are two parts of the same integral here. So this integral, okay, the integral minus infinity to 0 minus indicates the history period of the system, of the circuit or of the system, both are same. It indicates this first integral indicates the history period of the system. It means that it indicates the condition of the system at t equal to till t equal to 0 minus. And we already have defined in the previous lecture the conditions that are prevailing at t equal to 0 minus instant are the initial conditions of the system. And those initial conditions of the system are represented as I of 0 minus. Okay, therefore it indicates or not therefore, that is, okay, so that is, it indicates the initial condition in the system, therefore I can write integration 1 over L minus infinity to 0 minus VL dt is equals to IL of 0, and it is IL of 0 minus. So therefore I can write IL of t, okay? Therefore IL of t is equals to, first I will write the initial condition IL of 0 minus plus 1 over L integration 0 minus to t VL. Now as t approaches infinity, it is considered as the steady state condition of the system. And already we have defined initially, under steady state condition, my inductor is behaving as the short circuit. So I need not to know now what is happening under steady state condition. I want to know what is happening at switching condition, at the time of switching. What is happening at the time of switching? Now I have a initial condition current, okay, initial current IL of 0 minus, which is indicating the current at t equal to 0 minus. So initial condition is IL of 0 minus. Whether it is a 0, whether it is some finite value, it all depends. Okay, but I have considered in the general expression of the total current of an inductor what initial condition is. Now I know what has happened after the switch is closed at steady state condition is. I have this current IL of 0 minus before the switch has operated. I already have known that after switch has operated and when the t is under steady state, t tending to infinity means steady state condition. Under steady state condition, what happened to inductor? It is operating as a short circuit. Now I want to know what exactly the inductor is behaving like at the time of switching. What does it mean? I want to know what has happened with the inductor at t or at the time instant just after the switching operation has been done. Just before the switching operation, I have initial condition. After the switching operation, when the steady state is attained, I have the condition of short circuit. Now I want to know what has happened to the inductor, what inductor behavior is just immediate after the switch has been operated. Okay, so now I want to substitute the time instant t equal to 0 plus and see what is the current in an inductor. The inductor current at t equal to 0 plus, what is it? It is the instant, that is immediately after switch is operated. Now substitute t equal to 0 plus in the above expression. So IL of 0 plus is equals to IL of 0 minus will remain as it is because it is initial condition, plus 1 over L integration 0 minus to 0 plus, because t equal to 0 plus now, VL dt. Now what does the second integral term is telling me? It is telling the current during switching operation. During switching, IL of 0 minus is the current just before switching. Okay, IL of 0 plus is the current just after switching. If you see the integral of the second term, the integral is from 0 minus to 0 plus. So 0 minus to 0 plus is the switching time. 0 minus to 0 plus is the switching time. I can write here as this indicates current during switching. Okay, it is the current when the switch is getting operated from t equal to 0 minus to t equal to 0 plus. Now what is that current? We should see. Now the switching time or the time for switching is assumed to be 0. In a very initial condition itself, at the initial time itself, I have assumed that switch operates in 0 time. Okay, so we know that switch operates in 0 time. So when switch operates in 0 time, what does it mean? Time taken to operate the switch is 0. It means dt is 0. Okay, it means dt is 0. Okay, so that is dt is 0. So when dt is 0, what about the second term? Therefore 1 over L integration 0 minus to 0 plus VL dt is 0. This is 0 only when t equal to 0 plus. Only when there is t equal to 0 plus. Now therefore I can write IL of 0 plus is equals to IL of 0 minus. This is an important deduction. So what does it say? Second term is becoming 0, therefore IL of 0 plus is equal to IL of 0 minus. What does it say? It is saying that the current immediately after the switching operation is same as the current just before the switching operation. If you see the circuit, the moment I close the switch, the source voltage get applied to the circuit, but the current in the inductor is not changing immediately after closing the switch. So what does this last expression mean here is, this expression says that the current in inductor does not change instantaneously. This is an important understanding. The current in inductor does not change instantaneously. Okay, so you can observe from this expression that the current immediately after the switching operation is same as the current just before the switching operation. Even when the switch is operated, the current is not changing instantaneously. It may change after some time. The current may change after some time, but it is not changing instantaneously. Okay? So this equation, I can take this as equation 3. I will say that from 3, current in inductor just before switching is equal to current immediately after switching. Okay? So with this, what I can conclude is current in inductor does not change instantaneously. It does not change instantaneously. This is an important expression. So now go back to the inductor analysis with AC circuits, what we already have studied. What you concluded there? That current lags behind the voltage, right? We have seen this already in inductance for an AC. Current lags behind voltage. Why current has to lag behind voltage? The reason is here. Because by the nature of inductance, the inductor current will not change instantaneously. The voltage applied to the inductor will change instantaneously. If the applied voltage is varying with the time, simultaneously the voltage across inductor is also varying with time. But the current flowing through the inductor is not varying simultaneously with the time of voltage. It takes some time to come to that particular value, and that we call it as lag. The reason why current lags behind the voltage in an inductor is the inductor is incapable of changing its current through it instantaneously. It doesn't change its current instantaneously through it. That is the reason why the current lags behind voltage in an inductor. Okay, so this is the mathematical proof that current lags behind voltage in an inductor, or the current in an inductor doesn't change instantaneously. If I consider the voltage expression, I will rewrite the voltage expression here. Now what already we have seen, equals to L dIL by dt. Now we have seen under steady state condition the voltage becomes 0. This already we have established. At steady state VL equals to 0. Therefore inductor acts as short circuit. Now I want to know what is happening at the time of switching. So at the time of switching, my dt is equals to 0, because I have assumed switch operates at 0 time. Therefore my dt is equals to 0. Then at the time of switching, dt is equals to 0. Therefore what about my VL? Is tending to infinity. VL is tending to infinity. As VL is tending to infinity, it is definite that it is not operating as a short circuit. See, there are two behaviors of the inductor. Under steady state condition, my inductor is operating as a short circuit. At switching condition, my inductor voltage is tending to infinity. So when the voltage is high, definitely it is not short circuit. And when the voltage is infinite, I consider it as open circuit. So what I can say here, at the time of switching, or at t equals to 0 plus instant, just immediately after the switching action has taken place, at t equal to 0 plus, inductor act as open circuit. Now one more proof why it act as open circuit is hidden in the derivation what already we have seen. You go back to the split of integration. You take what is this integral. So this integral is the expression that is indicating the current at the time of switching. This integral indicates the current at the time of switching. So this integral is 0 at the time of switching because dt is 0. When does the current become 0? When there is no path for its flow. That is, when there is open circuit. Right? So this is one more proof that the inductor is behaving as open circuit during switching condition. Second proof here, the voltage is tending to infinity during switching condition. So both expressions are telling me the same thing. So only I told in one of the previous lecture that mathematics is speaking something to us. We should be able to understanding it. We should understand what my equations are telling me. Okay, the above expression, the integral expression is one such expression which is I have splitted one integration into two. But what each term is telling me is very important. So if we study the electrical subjects, visualizing what the mathematics is speaking to us, then you will appreciate the beauty of electrical science. Here, now the inductor is behaving differently at different conditions.